Good morning. If you joined us earlier and yet during yesterday's sessions, welcome back. If this is the first session, thank you for joining us and welcome to session 4 of 6 of the Water Bootcamp. The bootcamp covered hydrology, where your water comes from, and surface water rights yesterday. This session will cover groundwater, and following this, there'll be a session on CV salts and blueprint for water in the San Joaquin Valley. These sessions are being recorded and will be available for viewing on your own via the World Ag Expo show portal until February 28th. These sessions are brought to you by the California Water Institute at Fresno State, whose mission is to engage the San Joaquin Valley, California, and the world with Fresno State faculty, staff, and students in the pursuit of sustainable water resource management solutions through outreach, research, and education. The California Water Institute wants to give a special thanks to the World Ag Expo for allowing us to present this information. We wish we were in person with you in Tulare this morning, but hope that we're able to do so next year. Questions will be taken at the end of the session, so please feel free to add them to the chat function on Zoom or on the World Ag Expo show portal as we go along. The session speakers are CWI Interim Director Cordy Qualley and myself, Laura Ramos, Programs Manager for the Center. This session will focus on groundwater and will begin with some explanations on groundwater quality, including contamination and treatment. Then we'll move on to groundwater quantity, which will include distribution and subsidence, and will be followed by regulations and recharge. To begin the session, Cordy Qualley will speak to you about groundwater contamination.
Thanks, Laura. Good morning to everyone, and thank you for coming again today to hear our presentation. So groundwater contamination is a problem in the San Joaquin Valley. For most of us who use groundwater as our sole source for drinking water, we must contend with it all the time. Groundwater contamination generally occurs in one of two different ways. First way is where we have inadvertently or on purpose dumped contaminant on the ground surface, sometimes many years ago when we didn't realize that these contaminant sources can be mobilized by water and basically move through the ground system and into the groundwater aquifer. Many times we thought that these contaminants would be absorbed or contained within the soil matrix and not go all as far down or into the groundwater table, but many of them, because they were so soluble, did that, or if they weren't soluble, they were able to move under their own ability, their own gravity, pull of gravity down into the groundwater table and mixed in with the groundwater, and were then subsequently create plumes, as you can see here, that are moved towards the well by the action of the well, creating a depression in the groundwater table at the well, which creates a down gradient and pulls the plume into the well, where it's extracted by the pump and pumped into the distribution system. And so, first off, our first line of defense here is to make sure that we do not allow contaminants to move into the groundwater. Once they're there, they're incredibly hard to clean up and basically requires a very extensive and expensive extraction and treatment system. The common contaminants in the San Joaquin Valley are arsenic, selenium, salts, nitrates, and nitrogen, pesticides and herbicides. Some are organophosphates and water-soluble compounds such as 1,2,3-dibromo-3-chloropropane, also known as DBCP, and then your trichloropropane, the most notable of which is 1,2,3-TCP. All of these contaminants are to certain concentrations within our groundwater in the San Joaquin Valley. Not all of them are detectable at this point, but there are the problem with these types of contaminants is they do move around in plumes, and as they end up with a down gradient that pulls them into a well, they will eventually migrate in that direction. The one that's a primary concern in the valley right now is the 1,2,3-TCP, which is showing up. It has a very low MCL, but from the state of California, California is one of the few states that regulates the amount of trichloropropane that can be in the water, in your drinking water, because they feel like it's highly carcinogenic. Um, so many wells are starting to show up with 1,2,3 TCP and creating a need to treat that water before it's consumed. The problem with TCP is it cannot be removed easily. Well, it can be removed somewhat easily, but you can't remove it by boiling or those types of things, because actually as you boil it, you aerate it, and then it is still a carcinogenic substance that can cause problems for you to breathe or on your skin. So I'm going to show you a series of slides here from the USGS that show levels of these types of contaminants in the groundwater in the San Joaquin Valley as pulled up by well data and testing of water from wells. And the first one, and I've indicated on here where Tulare is, so you kind of have a point of reference on the map. The first one that we're going to look at are nutrients, and these are things like nitrogens and nitrates. They leach into the soil from the use of fertilizers, and they are carried by the groundwater as it percolates down into the groundwater table, and then start to diffuse into the groundwater there. And you can see that many of these glyphs in here, they represent either private wells or public wells, and they are in the many of them are in the blue and the yellow colors, as you can see in here. So a lot of nutrient nitrates and nitrogen and nitrate contaminants in the groundwater of the valley, and that's there primarily because of either natural occurring nitrogen in the soil that's leached down or the presence of fertilizers. The second one we're going to talk about are fumigants, and these happen to be those DBCP and 1,2,3 trichloropropane types of contaminants. You can see that they are both, again, private wells and public wells, and the colors range from clear up from cyan to a green to a yellow. And you can see that even though there are many clear glyphs in here that are indicating that there's no DBCP or fumigant tri 1,2,3 TCP contaminant, there are still a significant number of the colored glyphs that are showing up. And probably as we move through time, you're going to see more and more of these clear glyphs turn to a color. The third one we're going to look at are herbicides and herbicide degradants, which are just as herbicides that are applied to the ground, and also pesticides that are applied to the farming, to the crops. You'll start to see those residuals of those pesticides and herbicides leach into the groundwater soil through movement of precipitation onto the crops, and then percolation and pickup of those degradants by the percolated water as it moves down into the groundwater table. And again, you can see that there are significant numbers of these wells that are showing significant amount of contaminants picked up by them in samples. Basically, what we're saying is that groundwater is a very precious resource for us, and it does, but the problem is it's at the bottom of the bathtub, and so anything that's above it and ultimately ends up down there, and we need to be very careful about how we treat our soils and what we put on the soil so that we make sure that it doesn't end up in our groundwater. So once it gets down there into the groundwater, we have some capabilities for treating. And you can see here a graphic that was provided by the federal government that basically shows the typical ways for treating groundwater contamination, which tend to be those organophosphates or those uh, volatile organics that end up in the groundwater. And you can see that these extraction wells here indicate wells that are either there for treatment, or they could be extraction wells that are used by a city or your own private well to provide drinking water. Typically, they'll go into a holding tank and then be sent through a series of treatment processes to remove these organic compounds. The primary methods for removing the organic compounds, which would be your 1,2,3-TCP and your DBCP, is air stripping, where basically the water is exposed to a air device that aerates the water and helps helps those volatile organics dissipate. Then it's sent through what we call GAC, or granulated activated carbon, which is basically a carbon material that has an affinity for these uh, volatile organic compounds and organophosphates, and they get absorbed, add to the surfaces of this granulated activated carbon and remain there, and which then pulls them out of the ground, out of the water, and it's then treated and sent on to either a drinking water system, or in some cases re-injected back into the ground. For the removal of nitrates, there are three primary ways of doing that. One is through resin ion exchange. The most prevalent and popular one is reverse osmosis. And then third, there is a patented biological removal system that's available that is supposed to be highly effective and very inexpensive to operate. It's shown over here on the left, and it's a patented treatment system that provides a biological bioreactor where bacteria are used to consume the nitrate and produce a harmless byproduct. The other option that's shown over here on the right is the reverse osmosis, which basically you're using a membrane and forcing the water through the membrane, and that membrane is so small in its size that it removes the nitrate and nitrogen molecules out of the water as it's forced through the membrane. And ion exchange is typically more of a local water treatment system. So you might have like a water softener tank that has ion exchange in it, and it would remove that, use that ion reaction to take the nitrogen and substitute it for another ion, and remove it from the water that way. So that is pretty much how we the contamination that we find in the groundwater in the San Joaquin Valley and the primary ways of removing it. And so Laura's going to now continue on the discussion on groundwater.
Thank you, Cordy. As Cordy talked about the plumes and how water moves around or contaminants move around our underground aquifers, I wanted to start with the discussion first with distribution. So as if you were in the session about distributing surface water, we are able to move it around. They're very similar with our groundwater. It's just we don't normally move it around to such distance. So the groundwater is distributed to three primary places. One is a private residential home that only has a private well for its water source. It can be moved, pumped from a municipality or a city to their treatment plants and then distributed to the individual homes, or it can be pumped on a farm and distributed throughout the farm. And so with that distribution, we're thinking of how that water is being distributed from under the ground to above ground and then moving it around. During a couple of the sessions yesterday, you heard the word subsidence from either Cordy and I or both of us in the different presentations. So this photograph or this graphic depicts a little bit about what subsidence is. If you think about subsidence, think of a sponge that you use to wash dishes. When it gets dry, it tends to get smaller and just very hard. But then when you put water on it to use it, it kind of plumps up and comes back to its original state. Unfortunately, our groundwater is not exactly the same, but very similar, depending on the type of soil that is underneath and where the water is flowing. Some soil is able to come back to a similar state, but not 100% to where it used to be before we pumped all the water, with the exception of any of the clay, the Corcoran clay or any other type of clay. Once it is compacted, it is not able to come back. And so through years of extracting water from the groundwater, from groundwater aquifers, our land has subsided. So if you see the graphic on the left, shows a flat surface, and on the right, it shows almost like a downhill, but that isn't a downhill. It's actually the ground subsiding. As Cordy's photograph from a couple days ago showed how the light pole was showing where in different areas it was moving down and how far it was moving down. That is very similar to what's happening in this depiction. And with subsidence come multiple problems, including infrastructure problems. As you can tell, if a road was not made to be a downhill, is now a downhill, it's going to have some infrastructure issues. Canals, bridges are now not going to be at the level that they were made, or the consistency that they were engineered or built to be, because that ground is no longer where it originally was. And one of the biggest side effects of subsidence is that we lose storage space. So we tend to do some groundwater recharge, or even naturally with rains, we've been able to put water back into our ground. But if our ground is compacted, it no longer has the space that it once did. So we lose that space due to subsidence. Because of one of the reasons is subsidence, but groundwater levels and quantities and quality has been an issue in California for years. And so in 2014, a law was passed that is now known as the Sustainable Groundwater Management Act, and it has 6 desirable results. So you might have heard them as undesirable results, but I'm going to go on the opposite side and say that Sigma is going to cause some desirable results. So some of the desirable results are that we increase our groundwater levels, that we increase our groundwater storage, that we reduce saltwater intrusion, that we increase our water quality, that we decrease our land subsidence, and that we increase or maintain the interaction between surface and groundwater. And the law we're going to go over a timeline, but it has 20 years for this areas to become sustainable. So the very first step was in 2015, and it was to develop a map that depicted the critically overdrafted basins. And so as you see from the map, we have multiple colors representing the different levels of overdraft that had occurred over years. The ones that are in red are critically overdrafted, and then the kind of orangey are high priority, then you have low priority and medium priority, because their groundwater level are not as in danger as the overdrafted ones. So in 2015, this map was developed and determined the prioritization. In 2016, DWR adopted regulations for evaluating groundwater plans. So each of those areas, let me go back, each of these areas, there was a basin, and within each of those basins, groups were created that are called this groundwater agencies. And these agencies were to develop a plan on how that area, or that basin, that group's geographical area was going to be sustainable and have their sustainability plans. Though the groundwater sustainability agencies were formed in 2017. And then by 2020, each of those agencies were to develop a sustainable groundwater agency plan. And so for the high and medium priority basins, they were due in 2020. Following that timeline, the sustainable groundwater agencies that are critically and overdrafted basins are to achieve sustainability by 2040. That doesn't mean that they don't, they submitted their plan and 20 years later, they'll figure it out. There's actually milestones along the way and some reporting that needs to be done to make sure that you are going to achieve sustainability by 2040 and not that you start closer to the end. So some of the ways that we can become sustainable, or one of the solutions is to have in those plans is to do groundwater recharge projects. So groundwater recharge projects are land that is designated specifically to recharge the underground aquifer. And so these areas are specifically ones that have been identified to have great soils that the water will penetrate quickly and move down the aquifer quickly and won't stay on the surface for long and create other problems. Groundwater recharge basins can be in a city, they can be in a farm. An individual farmer can place one in their farm on their own, or a irrigation district or a water district can do one. Or in this case, this photo is from Leaky Acres near in between Fresno and the city of Clovis along Freeway 168 and Ashland area. So if you're going up to Shaver Lake or some of that area and you look to your right, you'll see these groundwater basins, and there are a project from the city of Fresno. So in years when there is excess water or there's flooding, some of that water is placed in these basins from surface water that is available is placed in these basins to help recharge the underground aquifer and be able to be used in later years. This is not the only way that we can recharge the underground aquifer. This one takes land, and it means that land needs to be focused on that area, but also you can identify soils and areas where you can put underground water recharge. And so this is a technology that is fairly new. And in this photo, you see some of the pipes and the technology being installed underground. So you won't be able to see much of it other than the machine creating the trench to install the technology underground. Some of the benefits of these are that you don't have to take land out of production, or you don't have to have a land designated for that. You can actually plant annual crops or tree crops above it, and it won't damage the root zone because these are installed lower than the root zone. And there's multiple benefits to this technology, and it's fairly new. So Fresno State and the California Water Institute are currently doing a research project on underground water recharge on the Fresno State farm, and we hope to get great results from it and just provide it as an additional option for groundwater recharge. And it needs to be a focus of some of the plans that go into effect in the next couple of years to help with some of that groundwater issue. Thank you for listening to this information. We hope you found it useful. And at this time, we will address questions submitted via the chat. It is not too late to submit your questions. Please add them to the chat function in Zoom or via the World Ag Expo show portal. This boot camp covered hydrology, where your water comes from, and surface water rights yesterday. Thank you for joining and listening to the groundwater presentation. And we will follow this with a central CV salts presentation, as well as a blueprint for water in the San Joaquin Valley that we hope you're able to join. All sessions are being recorded and will be available via the World Ag Expo show portal until February 28th. Thank you.